Hi, everybody. Thanks so much for having me here. So I wanted to talk about standardizing signals in TC39. This is a particular proposal that I'm working on with a number of other colleagues. We have a logo for it even, that you could see, drawn by Anna from the Ehrenberg community. So I'm a developer at Bloomberg, previously at companies where Shane and Ujjwal worked. Working in the JavaScript infrastructure and tooling team to modernize JavaScript usage in developing the Bloomberg terminal. I've been part of TC39 since 2016, and that gave me the opportunity to work on a number of proposals like BigInt and private fields and methods. I'm also working in ECMA administration, so ECMA International being the body that governs the way that TC39 works at this very high level, allowing it to produce standards, and so helping to make sure that that provides a good support mechanism. And I live in New York City after previously living in coastal Catalonia. That's the very small piece of coastline that my town has. It's sort of triangle-shaped. The Bloomberg terminal is a piece of software that lets financial industry professionals get information about financial markets to help facilitate decision-making. It has a very complex UI, and internally, it's based on Chromium. So even though it's not a website, a lot of these important web front-end techniques are still relevant. And the core of these techniques, many of them, if you're maintaining a front-end application with a UI framework, is to keep the DOM up to date with the data. So we have all these big graphs and charts and tables, and how do we make sure that as the data is delivered, it can be put on the screen? And the answer provided by typical modern UI frameworks is to make sure that the view, the stuff on the screen, is a pure function of the model. So model view controller, kind of the old way to talk about this stuff, but it's representing the state. So if it's a function that's what translates from the data to the screen, how do we evaluate that function? There are two basic techniques. One is traditionally called immediate mode, sometimes used to render video games, where each frame, each time the screen is going to show something, you re-render the whole screen, and then you bleed it onto the screen. You just copy all the information straight to the screen. The other paradigm is retained mode, where by default the screen continues to show what it showed last frame, but then you just change the parts that should change. So the goal of fine-grained pull-based reactivity is to somehow bridge these. We want retained mode performance while having immediate mode semantics. We want it to be that you program in terms of what is the function from the state to the DOM, and then instead it only reevaluates and changes the little parts of it that are relevant to change. And signals are a mechanism that we're proposing to do this. Signals consist of these little cells of data. So instead of just dealing with variables, you deal with a signal so that it can help track what's changing. Signals in this API that we're proposing in TC39 have a constructor and a get method. In computed signals have a constructor where you pass a function, and then you can get it, and getting it just calls that function. And then there's a watcher, which allows you to watch changes to computed or state signal. So I'm going to go through an example of how this can be used to build a UI. The thing about having signals as part of a shared standard is that now the model can be independent of the view. We want to enable model-view separation, and once they're independent, they should also be independent of frameworks as well. So here's an example of a simple reactive data structure. We have a counter, and you can get the counter or increment the counter, or see whether it's even or odd. So by calculating some of these things in computed signals, this information is cached so that it can be updated on the screen only when necessary. And it could be integrated into different frameworks like Preact and Vue, which do already have sort of signal-based rendering models, just into their existing template systems. So these templating systems make it a declarative functional way to show what your UI contains just by filling in the blanks. And it makes it so that when you click the button, the right piece is the UI update. But for example, if we made a +2 button, we incremented it twice, it would leave the parity in place once it can calculate that the is-even thing didn't change. It doesn't even need to recalculate parity because the caching can recognize the similarity. So there are a number of different algorithms that you can use to evaluate signals. In particular, why is it an algorithm at all? Because you might think, okay, I update seconds, and then that goes to the two things that use it and updates them, and then recursively. So then that should make sure everything is updated. But this algorithm is actually broken. So in the naive, eager, push-based algorithm, if you have your state, which is seconds, and then you go to the things that use it, which is this G and T. And this example is just from a very well-written Wikipedia article on reactivity. If you update G first, because you're just going to visit the children in arbitrary order, then it's actually going to see, after the first evaluation, so this gets initialized to 1, and then this becomes initialized to true. But if you update seconds, so it becomes 1 and 1, then G becomes false momentarily until later it updates T. So this is called a glitch because the program gets into an inconsistent state. And the solution is to use pull-based evaluation and topological sorting of dependencies. So instead of recalculating when we write to seconds, instead it recalculates when someone tries to read G. And it does this by looking at all the dependencies, recursing upward, and then topologically sorting them so that nothing is used before it's recalculated. That ensures that the consistency problems are solved. To do this, you have to be able to track invalidation. And there are a couple different algorithms for tracking invalidation. One is to use generation numbers. So every time something changes, you kind of count up on a global counter. And you can see if something is invalid, a computed signal is invalid, if it depends on something that's newer than it. Another algorithm is to kind of push dirtiness through these forward edges. So if you change A, and then these various other things depend on it, then that could mark C and B dirty, and the subsequent things might be dirty, depending on whether C or B evaluates to new values. And then when reading F, it will gradually iterate through the graph, reevaluating things until everything is understood. The important thing is there are multiple algorithms, but they have the same observable behavior. When I say observable, I mean in those computed signals, there are JavaScript callbacks, and those JavaScript callbacks get run in the same order and the same number of times at the same time, regardless of which algorithm is used. So ultimately, we have a situation where many frameworks independently reinvented this, and it's sort of like the natural phenomenon of carnicization, which is where many different crustaceans independently evolved a similar body plan to crabs because it works well for certain lifestyles. And many frameworks independently arrived at signals. They were all trying to solve this problem that I described at the beginning, how to make sure that the view is a function of the model without reevaluating that function every single time. And as they encountered problems like the glitch problem and how to accurately maintain the invalidation of signals to figure out what to recompute, fixing different bugs over time, this took people a long time to figure out, but eventually people came to really the same or very similar common answers. So we all got together to standardize the result, to share our common answer. So what does it mean to standardize signals? There was a project more than 10 years ago at this point called Promises A+. And that project was about standardizing promises. So how many people here have heard of promises? Okay, everybody, or almost. So great. Promises are ubiquitous in JavaScript because anything you want to do asynchronously returns a promise. In the old days, you had a callback that was passed in, but this becomes kind of unwieldy, becomes this callback hell people talked about. And so people wanted to, instead of having a callback that's called with a result, have a value that represents this pending result. And many different frameworks independently invented their own kind of promise. But they had somewhat similar APIs. They all had this then method to chain the results on. So the Promises A+ was a community standard to unify all the promise interfaces and make them compatible with each other. It was finding both a common interface and common meaning. And this was used, this was deployed with everybody converging even before it became part of the language. And then it became obvious, if we want promises in JavaScript, we should align with that. But with signals, we're really focusing on having common algorithms for this underlying reactivity graph. So different frameworks do have different ways of looking at things, but it's important that everyone can use this same model underneath, and then they can put different skins on top, and it's actually okay to differ. So the changes that engineers will need to apply when adopting standard signals will be nothing. Migration will be transparently handled by frameworks. And we're doing this effort through TC39. The JavaScript Standards Committee is part of ECMA. Earlier, we heard from Ujwal about how TC39 works. So just in April, I worked with people from Jatin, from Google, and Yehuda from Heroku on presenting signals to the JavaScript Standards Committee. And it achieved stage 1. So at this point, signals are on the table as something under discussion, but they're still very early discussion. So at this early stage, we're focusing on prototyping implementations of signals in order to figure out what to do, to see what we can get right or wrong about it. For example, we have a signal polyfill. We have an implementation of signals in JavaScript. This isn't a kind of a normal polyfill that's put onto the global object, but it's just a library that you can use that implements the signal API. And yeah, I worked on it with some colleagues at Bloomberg based on the Angular signals implementation. It's just kind of a wrapper around Angular signals. But we're encouraging more experimentation with other kinds of polyfills as well. You can play with it on NPM if you want, but please don't use it in production. It is buggy and unstable, and the API will change in the future. There are also libraries that can be built on top of signals. For the signals util library lets you, for example, decorate a field, even a private field, with TC39 standard decorators, and make it so that when you read or write that field, it's underneath a signal. So we don't actually want you to write .get and .set all around your code. There are various different abstractions that could be used, and this is just one of many possibilities for that. Or you could use a reactive object. This is common in many frameworks today that you, like ref in Vue. You can make an object which becomes a proxy, such that when you read or write properties, those are tracked as signals. So due to the auto-tracking mechanism, as we call it, within signals, the there doesn't have to be explicit threading through of the fact that there are signals, but the system just watches, and it can see that it's writing to a signal here when you write to a property of something that is a signal object. So signal utils you could also download and play with from NPM. And the other side of the coin is integrating signals into frameworks. So frameworks being things like Vue or Preact that help you render to HTML, to the DOM, your state. One experiment was done with integrating signals into Ember, but experiments have also been done with Vue and Lit and several other frameworks. And they found actually part of the polyfill was very slow. The part that I wrote, actually. So here's some graphs showing that. And also it's buggy, so there's room for improvement. You can work around these bugs, though. So yeah, this crab is kind of cooked. It's not in the perfect state, but we can improve things. We can. There's a lot to do, and I would encourage any of you who are interested to join the effort. Whether it is in terms of trying to use signals, working on the polyfill or the tests, giving feedback on anything. There's many different possible coding tasks or documentation tasks if anyone wants to join this open source project. So if you're interested, please join the Discord or Matrix channels that we have in a pinned issue on the repository. You can also join ECMA and TC39 to participate, though you don't need to be a member of ECMA to participate. And please come talk to me if you're interested in getting involved. So thank you, everyone.